We've been looking at kinetics of reactions this semester, and we're ready to look at what happens in some slightly more complicated cases. So for example, suppose we have this multi-step reaction. This is hydrogenation of an alkene. We know this is a catalytic reaction, and there's a particular way that we approach catalytic reactions that you'll see later on, but we're not going to get to that right now. We're just going to focus on the fact that this is a multi-step reaction and learn how we approach things like that. So I've got a number of steps here. And these are individual steps from one intermediate to the next. Those are called elementary reactions. So every time you've drawn a mechanism and you've drawn individual steps from one intermediate to the next, you're drawing elementary reactions. The useful thing about elementary reactions is that we can always predict the rate law for that individual step. The rate law for an individual step in a mechanism always depends on a rate constant and the concentrations of species needed for that step. Now, we're going to make some assumptions about this pathway. We're going to have to assume somewhere that there's a rate determining step. And the reason we're going to do that is because things simplify a lot. For instance, if we assume that that second step is the rate determining step, then we don't have to worry about the steps after that. They won't have any influence on the overall rate of the reaction because the rate of the reaction is being determined by the time we get to that bottleneck, that second step. So let's take a look at what we have in that case. Okay, so we only have these two steps now. And if we've got a multi-step reaction, there are a couple of different ways that we can go about determining the rate law. But I'm just going to show you a shortcut to one called the steady state approximation. The full treatment is the steady state approximation, but we're just going to do this shortcut that arrives at the answer. And the shortcut is that every rate law has a numerator. And to find the numerator, all you have to do is multiply the forward rate constants together, as well as concentrations of all the species that you need to carry out those forward steps. So that means we've got a forward step here of K1, and a second forward step that uses K2. And the species that we need to go through those steps are this tris-triphenylphosphine palladium, for that first step. For the second step, it's this bis-triphenylphosphine palladium and hydrogen. But this is an intermediate, this bis-triphenylphosphine palladium. And intermediates never show up in these rate laws. So we're going to ignore it, and we'll use the hydrogen, but not the palladium intermediate. Now, rate laws also have a denominator, and to find the denominator, you add up all the steps that consume the intermediates. So this is the intermediate, and there's a backward step that consumes it, and that's going to be this K-1 step. And it needs some triphenylphosphine, as well as the palladium intermediate. But again, the palladium intermediate doesn't show up in the rate law. There's another step that consumes that intermediate. That's this step here. Depends on K2, and it needs hydrogen. So there we are. That's the rate law for this multi-step reaction, given the assumptions that we've made. So how do we interpret that rate law? Here's the rate law again in the top left. And I'm going to consider two different factors that will influence the rate law. One of them is, how does the rate law vary with phosphine? Because phosphine is showing up in the denominator here. And if phosphine's in the denominator, that means the rate will always go down as we add more phosphine. Okay, so phosphine is an inhibitor. The more phosphine we have, the slower the reaction goes. there's some physical meaning for that. The physical interpretation would be that phosphine has to dissociate in this pathway to make room for the alkene to bind for the subsequent reaction to happen. And so adding more phosphine is going to make it less likely for the phosphine to dissociate. We're not going to get that open coordination site that we need. The hydrogen dependence is a little bit more subtle, and that's because the hydrogen shows up both in the numerator and the denominator. So that makes things a little tricky. And what we do in these kinds of cases is we look for what are called limiting cases. So we look for what happens when the hydrogen concentration is low, and we look for what happens when the hydrogen concentration is high. Now, when the hydrogen concentration is low, at some point, we can make the assumption that this right-hand term is a lot smaller than the left-hand term, just because this number is very small. And also, if K2 is the rate determining step, then K2 is a very small number as well. So a small rate constant means a slow step. So at low hydrogen concentration, that right-hand term is probably very small. And if you're adding two numbers together, and one of them is a whole lot bigger than the other, then the sum of those two numbers is always somewhere around the bigger number. In other words, we can ignore a small number if we're adding two numbers together, and one of them is much smaller than the other. So we'll just ignore this whole term. And what we get then is this much simpler relationship, where it's clear what the relationship with hydrogen concentration is. The more hydrogen we have, the faster the rate, because hydrogen is only in the numerator. On the other hand, at very high hydrogen concentrations, maybe the opposite is true. Maybe we could ignore that left-hand term because it's going to get much smaller eventually than the right-hand term. So we'll drop out that left-hand term and we're left with this relationship. But now things simplify because hydrogen can just be canceled from the top and the bottom, so can K2. And so we've got this relationship that has no hydrogen dependence at all. So at some point, as we've increased the amount of hydrogen, the rate stops depending on hydrogen concentration. This is called a saturation curve. So the implication here is that at some point, the system is saturated with hydrogen, and we can add more and more hydrogen if we want, but all the palladiums have already taken up hydrogen, so they don't need any more. And so they're just waiting for the reaction to go ahead and use up that hydrogen rather than accepting more hydrogen. So that's a little overview of steady state approximation, or at least a shortcut of it, and how we can interpret these more complicated rate laws that we get in multi-step reactions.